Imagine hurtling through the sky at Mach 25 with a 330,000-pound behemoth strapped to your back, and every single drop of fuel counts toward not just reaching orbit, but conquering the stars. One wrong turn in your flight path, and you burn through enough propellant to fill 3 Olympic swimming pools. Wasted. But what if I told you that SpaceX's Starship doesn't just fly, it dances with gravity itself to squeeze every last ounce of efficiency out of its massive fuel tanks? Welcome back to Rocketry, where we blast off into the engineering wizardry behind the world's most ambitious rocket. I'm your host, and today we're decoding how Starship's flight path is optimized for maximum fuel efficiency. Buckle up, this is going to be a wild ride through physics, fire, and futuristic flight paths. If you're new here, hit that subscribe button and join the 500,000-strong Rocketry crew exploring the cosmos one launch at a time. Let's start at the very beginning, because understanding fuel efficiency in rocketry is like understanding why your car gets better mileage on the highway than stop-and-go traffic. In spaceflight, fuel, or more precisely propellant, is the lifeblood. Starship, that stainless steel marvel standing 394 feet tall, guzzles about 2.6 million pounds of liquid methane and liquid oxygen just to get off the ground. That's enough meth-locks to power a small city for days. But unlike your daily commute, there's no gas station at 62 miles up. So every 1,000 feet per second of velocity you gain, or delta V in rocket speak, comes at a premium. The rocket equation, that brutal math from Konstantin Tsiolkovsky back in 1903, tells us efficiency boils down to exhaust velocity and mass ratio. For Starship's Raptor engines, we're talking specific impulse, or ISP, of around 327 seconds at sea level for the sea level variants, jumping to a whopping 350 seconds in vacuum for the vacuum-optimized ones. That's the measure of how much bang you get per pound of propellant. Higher ISP means less fuel burned for the same speed. But here's the kicker. Even with those monster numbers, getting to orbit requires about 30,800 feet per second of delta V, accounting for gravity losses, atmospheric drag, and steering. Waste even 1% of your propellant on inefficiencies, and you're looking at payloads slashed from 330,000 pounds to maybe 220,000. Or worse, mission failure. So how does Starship claw back those precious percentages? It all starts with the flight path, the invisible roadmap etched in the sky that turns brute force into ballet. Traditional rockets punch straight up like a boxer, fighting gravity head-on and bleeding fuel. But Starship, it plays smart. Enter the gravity turn, a deceptively simple maneuver that's the cornerstone of modern ascent optimization.
You've seen it in every launch video. The rocket lifts off vertically to clear the pad and thick lower atmosphere, then pitches over ever so slightly, maybe 1 to 2 degrees per second, and lets Earth's gravity do the heavy lifting. It's like rolling a marble down a hill instead of pushing it straight up the slope. By 6 miles altitude, Starship's already tilting to 45 degrees, trading vertical speed for horizontal. This minimizes gravity losses, which can eat up 3,300 to 4,900 feet per second of delta V on a straight shot. Quantify that. On Falcon 9, SpaceX shaved gravity losses to under 3,300 feet per second through precise gravity turns. And Starship takes it further. Simulations from pre-flight test 1 showed their optimized profile reduces total delta V demand by 5 to 7% compared to a 1950s-era ballistic trajectory. That's hundreds of thousands of pounds of propellant saved, enough to add an extra satellite or two to the stack. But wait, what happens when the air thickens the plot? Because down low, drag is the silent thief, robbing up to 650 feet per second if you're not careful. Picture this. You're climbing through the troposphere, where air density is like swimming through molasses. At Mach 1, just 15 seconds after liftoff, dynamic pressure peaks at over 4,300 pounds per square foot. That's the force trying to rip your fairing off. For Starship, with its 30-foot diameter and those 33 Raptors on the Super Heavy booster firing at 16.5 million pounds of thrust combined, drag could theoretically burn 110,000 to 220,000 pounds extra if the path isn't tuned just right. SpaceX's secret sauce? A meticulously modeled ascent corridor using real-time weather data and computational fluid dynamics. They aim for a drag-optimal angle of attack, keeping the vehicle at about 5 to 10 degrees nose up during the transonic phase, where shockwaves form like invisible walls. Data from IFT-4 in June 2024 revealed they throttled the engines down to 40% during max Q to ease through that pressure spike, saving an estimated 2 to 3% on propellant by avoiding structural stress and excess drag heating. And the numbers don't lie. Peak heating hits 2200 degrees Fahrenheit on the windward side, but by optimizing the path to hit Mach 1 at 7.5 miles instead of 6.2 miles, they cut aero losses by 15%. It's not just theory. Post-flight telemetry from IFT-5 showed the booster separated at 42 miles altitude with 92% of predicted efficiency, meaning only 8% losses to drag and gravity combined. That's wizard-level piloting without a pilot, all coded into the flight computer.
But hold on. We've cleared the atmosphere, but orbit isn't one yet. As Starship arcs toward the horizon, what's the cliffhanger that could doom the whole mission? It's the moment of truth, orbital insertion. One mistimed burn, and you're either splashing in the Indian Ocean or overshooting into a deadly reentry. Stay tuned, because next, we're diving into how SpaceX turns coast phases into fuel-saving gold mines. All right, we've escaped Earth's greedy grasp below 62 miles, and now Starship's in the black, coasting on a suborbital lob, belly flopping if it's the ship, or flipping for boost back if it's the booster. This is where efficiency goes cosmic. The flight path here isn't a straight line. It's a precisely calculated ellipse, tuned to Earth's rotation for that free 1,500 feet per second equatorial boost. Launching from Starbase in Boca Chica, you're already pocketing 1,000 to 1,300 feet per second from the planet's spin alone. During the coast, no engines fire, pure unpowered glide to save every gram. For the upper stage, that's about 6-7 minutes of silence after MECO, main engine cutoff, reaching apogee at 93 to 124 miles. But optimization shines in the relight. Raptor's vacuum variants with their 380-second ISP ignite for a 3-minute burn to circularize at 155 miles. The path? A home-in transfer tweak minimizing plane changes. Full orbital delta V? Around 25,600 feet per second after losses, but Starship's 3,600 feet per second reserve from propellant margins lets it handle 5-degree inclination tweaks without breaking a sweat, saving 22,000 to 44,000 pounds versus a dogleg maneuver. These coast optimizations mean Starship can loft 330,000 pounds to LEO on a single tank versus 265,000 for a less efficient path. Elor himself tweeted post-IFT3 that their sims predicted 95% fuel utilization and real flights are hitting 93%. That's the difference between a one-way ticket and reusable glory. Now let's geek out on the brains behind the brawn. Autonomous trajectory optimization. SpaceX doesn't hand-fly this. It's GNC. Guidance, navigation, and control software crunching 100 times per second. Using convex optimization algorithms, it solves for the path that minimizes the integral of thrusts squared over time. Yeah, it's math porn for rocket nerds. Constraints? Keep dynamic pressure under 7,250 pounds per square foot, acceleration below 4G for payloads, and heat flex at 285 BTU per square foot per second max. The software adjusted pitch rate by 0.5 degrees mid-ascent to counter a 6.5 foot per second wind shear, recovering 1.2% efficiency on the fly. And for the booster, that boost back burn, 3 engines fire for 20 seconds, arcing it back to the launch site with just 650 feet per second delta V. Landing accuracy within 33 feet thanks to path tweaks that shave 11,000 pounds off return propellant. It's like GPS for fireballs. But efficiency isn't just for Earth orbits. Starship's path mastery is Mars-bound. For interplanetary shots, they stack trajectories. Launch windows every 26 months, using a Type 1 home into Mars in 6 months, with 14,100 feet per second delta V from LEO. Optimization, refueling in orbit via 10 to 15 tanker flights, each docking with sub-millimeter precision to offload 330,000 pounds. Total propellant for TMI, Trans-Mars injection, 2.6 million pounds again, but the ascent path ensures 98% makes it to the depot. What if reentry flips the script? Starship's belly flop reentry skips traditional heat shields for lift, generating a 1-to-1 LD ratio to extend range by 620 miles, bleeding speed in the atmosphere like a space brake, saves 330 feet per second delta V on deorbit burns. From IFT-5 data, peak deceleration hit 2G over the Indian Ocean with propulsive landing using 3 sea-level Raptors at 50% throttle. Total fuel for landing, just 44,000 pounds. But imagine scaling this to a fleet, hundreds of starships dancing efficient paths to build a city on Mars. The savings? Trillions in the bank. Starship's flight path isn't just optimized, it's revolutionized. By blending gravity turns, real-time GNC, and aerobraking, SpaceX has turned an 11 million pound launch vehicle into a 100-flight reusable workhorse, dropping costs from $10,000 per pound to under $100. Facts check out. NASA's Artemis 3 will hitch a ride on HLS variant, with path efficiency enabling 88,000-pound lunar payloads. And for Starlink, V2 minis need precise 53-degree inclinations, hitting 99% success rates. We've covered the ascent arc, the cosmic coast, the software smarts, and the reentry romance. But here's the big reveal. All this adds up to a 20 to 25% overall propellant savings versus legacy rockets like SLS, which guzzles 4.4 million pounds for half the payload. That's why Starship's on track for weekly launches by 2026, per SpaceX roadmaps.
So what's next in this efficiency epic? Rumors swirl of nuclear thermal upper stages boosting ISP to 900 seconds, or AI-driven paths adapting to solar weather in real time. One thing's certain, the stars are calling, and Starship's flight path is the most fuel-smart ticket there. If this breakdown of Starship's sky-high efficiency lit your thrusters, smash that like button. It helps us reach more space junkies like you. Subscribe to Rocketry for weekly deep dives into rocketry's bleeding edge, from Raptor upgrades to reusable dreams. We're aiming for 1 million subs by Mars 2026. Join the mission. And don't forget to follow our Facebook page, Rocketry, for behind-the-scenes polls, live launch watches, and exclusive Q&As. Drop a comment. What's your biggest question on Starship's next flight? Let me know below. Until next blastoff, keep looking up. This is Rocketry, igniting curiosity one trajectory at a time.